Hello, and we are going to start the review now for June 10th for the Math 170 class here. And the topics we're going to be reviewing today are mostly going to be one topic covering limits, and then we're going to move on to derivatives shortly after. So I wanted to do a little bit from section 2.6 covering limits at infinity. And so the key thing that we really need to know for this is we have to understand that 1 over x, the limit of this, as x approaches infinity, is going to be equal to 0. Okay, and so this is going to happen because, when x is a number like, say, 10 here, right, 1 over x is 0.1. X is 100, 1 over x, 0.01, 1,000, 0.001. And so on and so forth. And as you can see, as x is going to get larger, your values for y are going to get closer and closer to 0. Okay. So now let's look. Say we have, actually, I'm going to get rid of it. Well, we were going to try to get rid of it. So let's just move it over here, out of our way a little bit. Okay, so now let's say we have the limit as x approaches negative infinity, 1 over x. So what happens here? We'll do our xy chart again to see. So x negative 10, negative 0.1, negative 100, negative 0.01, negative 1,000. Should just be 1. But as you can see, the exact same thing happens. Have to be 10,000 for that other one to be true. At any rate, though, same idea. This limit is going to equal 0. So even though you're going to negative infinity, so the numbers are going to approach 0, they're going to be negative. They're going to approach from the left, but still you're going to approach 0, whether you go to infinity or negative infinity. Okay, so let's use that fact to find a few other limits. Some things are a little more complicated as x goes to infinity. So now let's say the limit of x goes to infinity of 5 plus 1 over x. Okay, well, we know from our limit rules that we can just take the limits of these two things and just add them together. Some rule of limits. Okay, so this is going to be 5. It doesn't vary with x. So as x goes to infinity, that limit's going to stay 5. Okay, then we have 1 over x. We said as x goes to infinity that goes to 0. So our limit's 5. Okay, so another thing that they're going to do in this chapter is they're going to throw a rational function at you and they're going to ask you to evaluate it. Okay. And so now what we can do is we can use our limit laws from calculus. And this is going to tell us something that like 5x squared, 8x plus 3, okay? And then we get 3x, let's do 2, plus 2. Okay, so here, a little bit more complicated. What we're going to do is we're going to divide everything by every term, by the highest power in the denominator. So in our case, the highest power of x in the denominator. So our case, it's going to be x squared. So we're going to take the limit here. X goes to infinity. X squared over x squared. 8x squared. 8 over x squared plus 3 over x squared. Okay. Oh, that was strange. I can get rid of it. Oh, maybe I can't. Well, at any rate. So if you ignore the lines there, they're not super great, but because we divided every term by the same thing, x squared in this case, we haven't changed the actual value of the function. So now when we take these limits as x goes to infinity, right, we have 5 limit. That's going to give us 5x squared over x squared, which is just 5. Okay, so then we're going to have 5 over, we have 8x divided by x squared. Okay, so that leaves us 1x cancels, and then as x goes to infinity, that'll be 0. We have 3 over x squared, as x goes to infinity, that's 0. 3x squared over x squared is cancel, and then 2 over x squared goes to 0. Our limit is 5 over 3. If you'll remember from college algebra, the horizontal asymptote rule is that your leading terms, in this case, they're going to be x squared. The coefficients of those are going to be your limit. And now we can see why. It's because those other limits are going to go to 0. And so calculus allows us to really explain why and see how that's happening, which is, kind of cool. So let's move on a little bit from limits, and we're going to switch over to derivatives. I say move on to limit, but move on from limits, excuse me. The first thing we're going to do is we're going to use a limit to define derivative. And then we take the limit of the difference quotient as h goes to 0, and that gives us the derivative. This is section 3 in your book. Okay, and so what we're going to do in this one, now let's find, say, f of x is equal to x squared. Now to find the derivative, we're going to take the limit of the difference quotient. That is, and I'll put this in the corner, limit as h goes to 0, f of x plus h minus f of x all over h. Okay, so then f prime of x, our derivative here is going to be the limit as h goes to 0 of, so now we're going to put in x plus h, whole thing squared, right? Because we're just plugging in x plus h for our x's. Then minus f of x is just x squared. Okay, then that's all going to be over h. So obviously we can't take the limit yet because we have h in our denominator. So as the limit of h goes to 0, we can't just plug in 0 because we'd be divided by 0. That would lead to an infinite result, which we don't want. So what we're going to do is we're going to have to find a way to get h out of the denominator. So to do that, we'll begin by expanding x plus h squared. And so that's going to be a limit. Bring our limit sign with us. As h goes to 0, x squared plus 2xh plus h squared minus x squared from our f of x all over h again. Okay, so you'll notice that, we're going to look at sides. So notice that we have a positive x squared and a negative x squared, so those can cancel. And then we leave us with 2xh plus h squared all over h. And so one last step here. Factor out in h, we get x plus h over h. These cancel. Now we can take our limit. We plug in 0 for h. And, sorry, that was supposed to be 2x. And then we get 2x is our derivative for x squared. And so we found that using limits. And this will work for any kind of function that you can take the derivative of. And we are going to show a more complicated example now. Doing the same idea, we're going to use the limit of a difference quotient to find the derivative of the function. So now we're going to say f of x is going to be equal to, start that one over. So our f of x is going to be equal to square root of yeah, well, I kind of was hoping that would go away, but it didn't. And we're just going to start over one more time. Equal to the square root of x plus 3. Okay, so finally, and it still doesn't look that great, but we're just going to roll with it. So the square root of x plus 3. So now we're going to do f prime of x is equal to, so it'll be the square root of x plus h plus 3. Okay, and then we're going to subtract. We got to subtract the whole thing, the square root of x plus 3, all over h. So you can see right away, 3's would cancel here. And so, oh, we forgot to put a limit. Okay, so now let's bring our limit with us. H is going to go to 0. Our 3's will cancel. Now we have square root of x plus h minus the square root of x. Okay, now all over h. Okay, so this gives us, we have a radical expression, 1 minus the other. And so in order to get this h out of the denominator, the trick, I guess we could the technique, but we'll just call it a trick. The trick we're going to do here is we're going to apply by the conjugate of the radical expression. Okay, so we're going to take our limit. H goes to 0. H minus root x all over h. So now we're going to multiply top and bottom. Multiply top and bottom so we don't change things, x plus h. And then we're going to be plus root x. X plus h plus root x. Okay, so the conjugate is that same expression, but we're just going to change the sign. Okay, so we do that. We get a difference of squares as well. And so we're going to end up with this here, right? These two things, you square those, we're going to multiply them together. They just come out to be x plus h, right? And then when we have a difference of squares, our middle terms disappear, and we're going to get the square root of x times the square root of x, and it's going to be minus x. Because when you this term here and this term here, see when you square these things, you get x back, okay, over h, and this h is going to be multiplied by the whole thing that we just multiplied by. So it'll be the square root of x plus h plus the square root of x. All right. And so you'll notice again, now we have these x's cancel, right? And that's going to leave us with an h up top. So let's put that here, bring our limit sign with us. Our h goes to 0. And then we're going to get h over h square root x plus h plus the square root of x. So now we see our h's canceled. The ones at the denominator and the numerator. Okay, so now we're going to end up with, we have 1 limit, and h goes to 0 of 1 over square root of x plus h plus the square root of x. So now you'll notice that when we plug in h, we're no longer dividing by 0. We don't have any discontinuity. So we can just do that. And we're going to get 1 over, we can drop our limit sign now since we're just going to be able to plug in the 0 for h. And so x0, of course, is the square root of x plus 0 is the square root of x plus the square root of x. And then that tells us that our derivative, the square root of x plus 3, is going to be 1 over 2 square roots of x. And that's the correct answer. So we're using the concept of limits. We're applying it to the difference function, or the difference quotient, excuse me. We take that limit, that gives us the derivative. So this is a very long and complex way to find a derivative, but in Calculus Math 170, it is something that they expect you to know, so it's worth going over. Now in the sections moving forward, they're going to teach you rules and make taking derivatives quite a bit simpler. And after you learn this and learn the basics of it, doing derivatives should be a lot easier than this. And it is a very useful thing going forward. So anyway, I hope this was helpful, and hopefully I'll see you next week.